Okay, so now last part of the presentation is calling C functions from R. And this also you can take advantage of these libraries because you can build with any functions. MKL and OpenBlast I like because they use the same calls to, Blast is actually a Fortran library, and there's a lot of different interfaces to Blast. MKL and OpenBlast use the same calls. So for double precision general matrix multiplication, it's this dgem with an underscore, calls the Fortran function, and both of them can compile this and they recognize it and don't complain. So I generally write in this style so that I can do either one and see which one's faster. But once you do have C code and you want to use it in R, there's two ways. This way is a little more typical of C coding, and if you're building a shared library for use in programs other than R, you might want to do this. Functions don't return anything. Void means it doesn't give you back a value. It's just empty. Your function name, and then R can only pass pointers. So if you ever see C coding, you can either do pointers, you can actually send values where it'll copy it over and give it to the function. But the actual better way of using C from R is to use, you need two headers, the R internals header and the R header, and then you can use these S expression pointers. R was really a descendant of S and S+, so it has a lot of these names that still show where it came from. Dot call is way faster, and it's much more like hacking R. You're really accessing the internals of what R can do, and that really gives you a big speed up. It can also only take pointers, but it's pointers to these values that are really R objects. These are what the R objects are really called in the background. And each one of these pointers can point to values which have, they may be integers or doubles or logical, things like that. But the benefit of writing functions like this is I can now create R objects in my C code. And I don't have to do, if you were to call one of these functions, your R wrapper would look like, it would alter all of these, give them a new label, and you'd do the $sign and call out which piece you want to pick out. And that also takes time. Some things to know that I'll show in these example programs. If you make one of these S expression pointers value, you need to protect it. You need to protect it from R killing it while you're using it. R's garbage collector won't try to get rid of anything that's passed as an argument because it knows that you're using it. But if you make something new, you have to protect it. And at the end, this N needs to match the number of protect statements, or else you'll get stack imbalance error in R when you try to call it. It's not too bad, and you know exactly it's an error that you know exactly what's wrong. You just go and count your statements over again. If you're just passing one number, like I want to pass an integer, in the C code, you just call as integer, and it'll convert it from this fancy R object into a C integer. And then these functions are also very useful. This gets you the pointer to the numeric part. So if you have a matrix in R, it's really, if you actually want the access to the matrix itself, you would use this real, and this will show up in the example C code. You have to return an S expression pointer, and if you really don't have anything to return, you return this nil value. It'll show up when you run it. It'll just say null in R. And don't alter objects that you pass as arguments. This can be really weird, and you can actually end up changing more objects than you think you are. If you say you store, like an example is if you assign 1 to X in R, then copy X to Y. Pass X as an argument and change it. It might also change Y in R, which just really weird, bad things can happen. So if you're ever going to alter something, duplicate it and then alter the copy. And then you'll just get rid of it. R's garbage collector will come wipe it out. But this is also why they say R functions are bad for memory, because if you pass a very large object and you want to alter it, R is always duplicating things in the background. That's why certain functions you'll just see if you watch your RAM on your computer, it'll just jump up. So first example, we're going to be using two things together, which in combination just turn out to be great. One is the GNU Scientific Library. It has a very, very fast way of generating random random variables. The Ziggurat implementation is very fast. There was an old library in R that would work with this implementation, but it doesn't work, I think, on 64-bit systems. It just spits out nonsense. It's really fast, but it just doesn't give anything that you can use. And so the goal here is to be able to use multi-core processors to generate random variables. And I chose these two topics because I'm a Bayesian, so half my life is spent multiplying matrices and the other half is spent generating random variables. So these are the things that have sped up my computation the most. But you can hopefully be inspired to use other things. OpenMP is a set of directives that you can put in your C code, which doesn't look like standard C code, but it tells the compiler to do things so that you don't have to do them by hand. And so you'll see it's just one line, and it can parallelize things for us. The one thing we have to be very careful for, the longest part of this code, is actually initializing the random number generators. Because as you know, if you do simulations, if you're setting a seed, you have to do a different seed for each run. And if you do things on multiple cores in parallel, you need to use a different seed. There's a couple approaches. The approach I take is to use the same style random number generator with different seeds. And so this is actually going to be the longest part of it. So now let's look at some C code. So these things in green in general are types, value types. And so we have for GSL, the random number generator, these are going to be global variables. And this I'm using as a global variable because when I load it into R, I want to keep generating from the same string in the random number generator. If I put this in a function, it might only get used once, and then every time I call it, it would redo it, and then I would have to count how many values I've used. So these need to be global. These are pointers. The star, a double pointer, is really an array of pointers. So this GSL RNG is really what's going to hold a vector of random number generators that we're going to use. So this is a function. So we're passing a seed and returning an S expression pointer. Seed I'm now converting using as integer. Just need some variables for loops and all that. I'm going to use the same random number generator that R uses just to compare, because some are faster than others, and so I don't really want to be unfair to R's R norm function. So we're going to use that. We're going to allocate size for the random number generators, the number of threads. Here I'm getting the maximum possible threads just in case you're going to use them, but I'll write a function where you get to choose the number of threads you use. This OMP set num threads you can actually use for a lot of things. MKL and OpenBlast use OpenMP, and so this would also affect if you do any blast calls. It might affect the number of cores that you use for those. Now the real assignment part is this, and this is the great part of OpenMP. I just tell it, give it #pragma, OMP parallel 4, and then there's some clauses here that tell it exactly what I want. I need to share this random number generator, and this actually doesn't really need to be shared the type because it's not changing, but I want to, when I loop through this vector, I want it to be shared. I want to be actually accessing the exact same elements. There's a private clause, and that makes a separate copy for each iteration. And this really doesn't take a long time. The only reason I'm parallelizing this is for memory purposes, because when I go, this OMP get thread num will tell me what core I'm using, and when I use it later to generate, I want the memory to be in the same place. I don't want the overall program to do this, and then when I split it off into separate threads, they might have memory in separate places. So this is just not completely necessary, but this sets up this vector of random number generators to use this type of random number generator, the Mercian twister, and then sets the seed and just increments it by the thread number. And then I return nothing. And so now I'm going to write a core function to do my actual generation. And this is just a C function. This one is never going to get called directly from R. I'm going to write a wrapper for it. But this is just generates n normals using NT cores on my processor and puts it into out V. And it uses it a pointer, so I'm not copying this. I'm just directly putting in my values where that actually exists in memory. And this pragma OMP parallel lets this loop be done in parallel. I tell it that I'm sharing my output vector and I'm sharing the random number generator. I need to share this so that when I step forward in each random number generator, I'm doing it for that entire vector. Or else, if I don't share this and it ends up being private, then I'll end up with all these copies and things really won't get incremented, which they need to. And this, num threads can tell it how many threads to use. And so all I do is for each element, I just generate a random Gaussian with this is a standard deviation, and I use the ziggurat method. This is a function from GSL. And I give it the element of the random number generator. I choose what thread I'm in, and I choose that random number generator out. And so if I want to call this, this is my wrapper for actually calling this from R. So this is the style I need to use in R. I just convert things to how I need it. I create my own S expression pointer, which I protect. And it's a vector of reals. This is doubles in R, and it's n long. Now, I use the real function to point to where the actual matrix is within this very complicated object. The matrix is this. So this is pointing, or the vector. This is pointing to the actual numbers that are in this S expression vector. And then I just generate normals and I put them in out v, which is actually in this result variable. I unprotect it and then I return the result. And now I'm going to compare it to R's standard R norm function and see the kind of speed up we got. And I'm going to compare it using, the processor has 6 cores, so I'll show you the comparison after, this is what I was talking about. Instead of using the R share library command, you can really just add FPIC and shared flags to the call you would normally use to compile a C function. FPIC is position independent code, which is really important if you're doing a shared library. Shared tells it to be a shared library. OpenMP is what we need for the parallelization. This is an optimization flag. This march is really the architecture of the processor. Equals native tells it to compile it to be best performance for what I'm running it on. LGSL is a flag to use that GSL library. And then I could write a wrapper in R, but this is a typical R code. I load a dynamic library. I use that initialization function to initialize everything. 1 is the seed I give it. And now this is a typical call. I can use that function directly using .call, and I pass the parameters. I pass it. Generates 20 normals using 1 core of my processor. And so this is what a typical call looks like. And so now to do a comparison, this is time relative to using R norm for different numbers of standard normals. And the gray is 1 core. And so as you can see, if I'm only doing 10 at a time, if I only use 1 core, I'm already twice as fast. I'm at half the time. If I use too many cores for small problems, that's when things get bad. But by the time I'm generating, say, 10,000 random normals, if I'm using all my cores, I'm at least 10 times as fast as using R norm. And this is huge. One thing you can also do, if you have the memory available and you need to generate a lot, generate them first and then pick out the values. Say you're using them in a loop. That's one possibility. If you don't want to do lots of small problems, you can do one large problem first, get it out of the way, and then use those values that you generate. But we can see huge, huge speed up. Even if you just set it at 1 core, you're going to be at 1/3 of the computing time, no matter how many normals you need to generate. But you can see huge advantages if you're generating a lot. The next example, I'll try to go through this. Sorry, I'm moving fast. All this code will be posted, and let me know if you have questions about how to use it.